Our topic is subgroup. We are already familiar with the concept of group G, O. Now from there we are getting one more term which is called subgroup. This is quite familiar with subset. Like suppose G, O is a group we have, then H is a non-empty subset of G. It's a non-empty subset of G. And if H is itself a group, then we will say that it is a subgroup. That means subgroup means subset plus group. H is a non-empty subset of G and it is itself a group. That means H also satisfied that four condition for being a group. Number 1, that closure property. Number 2, associative property. Number 3, identity property. And number 4, inverse property. That 4 property we had to satisfy for being a group. That 4 property is satisfied by H and H is a subset of G. Then we will say that H, O is a subgroup of G. Okay. Now for example we can consider this G equals Q. Q, plus. That means the set of rational numbers. Okay. And for H we are considering Z. Z, plus. Okay. Z means the set of integers. Then obviously Z is a subset of Q. We know that all integers are rational numbers. Rational number means they are of the form P by Q. Such type of terms. And Z, you know, these are 0, plus minus 1, plus minus 2 and so on. These are Z. Then obviously all of this belongs to this set. So Z is a subset of Q. And Z also satisfies all the 4 properties of being a group. That means Z is a subgroup of Q. Okay. Now similarly, we can prove few theorems on subgroup. Number 1 theorem is the identity element of H and G are same. Generally we denote the identity element of G by small e, right? We are saying that the same E will also be the identity element of H. We have to prove that. How to prove? Let EH be the identity element of H. And EG be the identity element of G. Okay, we have to prove that EH and EG are same. Now considering some H belongs to capital H, then what we can write by the property of identity element, that is EH composition H equals H composition EH equals H, right? This is by the property of identity element of H. Now again check, H is a subset of G, right? That means this H also belongs to G. So by the property of identity element of G, we can also write that EG composition H equals H composition EG equals H, right? So this is also H, this is also H. So take this one and this one. These are also equal. So H composition EH equals H composition EG. This will imply EH equals EG by left cancellation law. Okay. So both the identity elements for the group and the subgroup are same. Now moving to the next part of the theorem, that is the inverse element are also same. Inverse elements are also same. That means if you get for one element A, if the inverse in H is A dashed, then the inverse of A in G will also be the same thing. Okay, we have to prove it. So now for the proof of the theorem, we are choosing that A dashed is the inverse of A in H and A inverse is the inverse of A in G. Now what we have to prove? We have to prove this one and this one, this A dash and A inverse, both are same. Now by the property of H, what we can write? A dashed composition A equals A composition A dashed equals E, right? By the property of inverse of H. Similarly, by the property of inverse of G, what we can write? A inverse composition A equals A composition A inverse equals E. Then E and E both are same, so this equals this. Equate this one and this one. By left cancellation law, A dash equals A inverse. That means inverse elements are also same in both the group and the subgroup. Next we have another theorem which makes easier to check the subgroup property. That is, whenever we want to prove H is a subgroup, no need to check all the 4 properties. There are few smaller theorems to make it easier. So theorem number 1 states that if G is a group, and H is a subset of G, then H is a subgroup, if and only if A belongs to H, B belongs to H, this will imply AOB belongs to H and A inverse belongs to H. This is the required condition for being a subgroup. So whenever we have to prove that some subset of a group is also a subgroup, we will apply this theorem. Okay, we just have to prove, take 2 elements from the set H, then AOB also belongs to H and A inverse also belongs to H. Now we have to prove how this works. So for the proof, that means how these 2 conditions are equivalent to 4 conditions of being a group. We have to prove that. So let's take, first we are trying, this is check, it is given that A belongs to H, B belongs to H, this will imply AOB belongs to H. This is actually our closure property, right? So the first property is satisfied for being a group. Now next is associative property. Now associative property is a hereditary property. Associative property is a hereditary property. Hereditary property means which is satisfied by the set is also satisfied by its subset. This type of properties are called hereditary property. No need to prove that property. If it is satisfying for a set, it will also satisfy for its subset. So associative property is a hereditary property, so it will also be satisfied. That is number 2 is okay. Now we have to find out E, that is the identity property. So let's start. Now we have A belongs to H, this will imply A inverse belongs to H, right? Now choosing A and A inverse, then this will also imply A composition A inverse belongs to H. Now A composition A inverse means E, that is E belongs to H. That is the identity property is also satisfied. Okay, and by the given condition, inverse property is already satisfied because it is given that if A belongs to H, this will imply A inverse belongs to H. So inverse property is also satisfied. That means all the 4 properties of being a group is satisfied. So H is a subgroup of G. Okay. This is the rule of proving subgroup. We will use that later in so many examples and theorems. Okay. So this one is very important, this condition. Now we have one more condition to prove that this is a subgroup. So it is theorem 2. It states that GO is a group and H is a subgroup. Sorry, subset, not a subgroup. H is a subset of G. Then H is a subgroup if and only if A, B belongs to H, if this will imply A composition B inverse belongs to H. Okay, this is another important condition for proving a subgroup. We might use this one also later. So it states that whenever two elements belongs to H, the composition A composition B inverse also belongs to H. We have to prove that this one condition, this single condition, is equivalent to that four conditions for being a group. So let's prove it. At first we are starting with A belongs to H, comma A belongs to H, taking 2 times A. Okay. Then by the given condition it will show that A composition A inverse belongs to H, right? That means E belongs to H. So our identity property is satisfied now. The third property. Next, whenever E belongs to H and choosing any other elements A belongs to H, this will imply E composition A inverse belongs to H. That means E composition A inverse means A inverse. This belongs to H. So our inverse property is also satisfied. Whenever A belongs to H, A inverse belongs to H. That is our fourth property is okay. Now remaining two properties, closure and associative. Now associative, there is nothing to prove for the associativity part because it's a hereditary property. The only property left is to prove the closure property. So let's prove it. For that reason we are choosing A belongs to H and B inverse belongs to H. We already proved whenever B belongs to H, B inverse belongs to H, so we can choose it. B inverse belongs to H. This will imply A composition B inverse, its whole inverse, belongs to H. That means A composition B belongs to H. Okay. So our closure property is also satisfied. So, and associative is already satisfied by the hereditary property. That means four properties for being a subgroup is satisfied by the single condition. Okay. So this one is also very important to prove that H is a subgroup.